Hello and welcome to this session on CFD equations and numerical solutions. We've already gone through the lectures related with Introduction to CFD, where we got to know some fundamentals, some terminologies. We also saw what are the equations in fluid mechanics and heat transfer which need to be solved. And this is what we are expecting from you to be already familiar with for attending this lecture. And in this lecture, what you can expect from us is that you would get familiar with what is the difference between an exact and a numerical solution of the differential equations which govern a specific physics or phenomena. We'll also be learning one of these numerical scheme called the finite difference method in a bit more detail, but we'll also get an idea about what it looks like for other numerical schemes which you will hear in this lecture called finite volume or finite element methods. We'll also be learning what exactly is a grid doing in CFD? What is the purpose of a mesh? So I hope you'll be able to answer these questions, and the assignments that are given along with this lecture will help you to gauge your understanding of these specific topics. Well, we'll have a recap of the different equations that are involved in CFD during this lecture in the beginning, and we'll try to see how we can solve differential equations which consist of two types of equations, either ordinary differential equations or partial differential equations. Ordinary differential equations usually comprise of only a differentiation of dependent variables with respect to a single independent variable, unlike PDEs or partial differential equations which consist of the dependent variables. Things can be like velocity, temperature, pressure. These things have differentiation with respect to more than just one independent variable. Let's say time and space coordinates x, y, z. So that's why they are called partial differential equations. We'll see how to solve these equations. By the way, in CFD, we are dealing with PDEs, that's partial differential equations. We'll have an idea about the numerical methods in this regard. And we'll also have an overview of FDM and FVM and FEM methods, that is finite difference, finite volume, and finite element methods. We'll see more specifically in detail the finite difference method. So fine, let's look at what the equations are that we have tried to solve, that we are trying to solve in CFD. So we have this to be the general transport equation that you see on the top. This contains, as must have been discussed, a transient term, an advection term, a diffusion term on the right hand side, and a source term. So in CFD, we are trying to solve such a transport equation. A quantity phi is getting transported by the velocity field, by its propensity to get diffused, that's the diffusion term. And if there are sources of this quantity phi or this property phi, then this also adds on, and the rate of change of that is being governed by this first term on the left hand side. So we just replace the value of phi to be 1, or in the other case u, v and w, and that gives us the flow equations. The flow equations consisting of the continuity and the three momentum equations, which is primarily Newton's second law being applied along three directions, x, y and z. In addition to this, we may also have situations where we are interested to solve the energy equation. So therefore we have either a thermal energy equation or a total energy equation. When I say total energy, there can be an exchange of mechanical and thermal energy. In that case, this phi might look a bit different, but if say we are just interested in heat transfer and this is not really going to influence drastically the continuity and momentum equation solutions, in that case we can say that this can be solved independently, and that's a thermal energy equation. In addition to this, of course, we have other modeling equations. In some cases we may have multiple species being injected into the domain, so we have different mass fractions of the species as well being modeled. In some cases we may also have to solve a mixture fraction equation if we are also including such a combustion model. And in some cases your properties might be functions of temperature, so you might be solving not just transport equations, you might be also solving some additional scalar equations or algebraic equations But overall, this is what the equations looks like. So overall, the the message that we can take from this slide is that we are solving transport equations in CFD. They consist of the continuity, the three momentum equations being the flow equations, and additional equations as and when required in a specific analysis. So basically, in CFD, we are trying to solve these governing equations which govern the flow of fluid or heat or any other related phenomena. And the most general form of these equations is called the Navier-Stokes equation, which is applicable for Newtonian fluids. I guess you have come across this term in the previous lecture on fluid mechanics. And this can handle a wide range of physics. We have a simplified version of it, which is called the incompressible Navier-Stokes equation, where the density term is constant, does not vary with respect to the pressure of the flow. And in this case, the energy equation is completely uncoupled or is completely independent of the continuity and the momentum equations. We have a still more simplified form of the Navier-Stokes equation, which does not contain the viscous terms or the diffusion term that you can remember from the transport equation. That's the Euler equations. So all the momentum and the continuity and the energy equations do not contain that diffusion term. That's the Euler equations. And we'll see that we can actually arrive at a simple solution quite quickly, quite fast, with the Euler solution of a given problem. In addition to this, depending upon the model, we may have additional equations for turbulence. In some cases, we might be solving equations for the motion of particles inside the fluid domain. That's called the discrete phase equations for particles. Or if we are interested in modeling multiple species in a flow, that even a gaseous medium, let's say a gas phase, is consisting of different species. This can also be the case. And in that case, we are solving additional equations. So that's what the Navier-Stokes equation looks like. I guess this has been discussed already. So you can see the continuity equation containing the density. By the way, all these equations are in the differential form that you can see on the screen here. I'm sure that you're familiar with the differential and the integral form of these equations. The momentum equation, as you can see here, it has been simplified using the continuity equation, and you have the density term therefore coming out of it. And we have on the right hand side, in addition to the viscous terms, we also have a pressure gradient term, which is also present in the momentum equation, and the last term being the source term or the body force term, because we are speaking about the momentum equation. So we have mass into acceleration, somehow a representation of mass into acceleration being equal to the sum of the surface forces, that's the pressure gradient, and the viscous terms that you can see here, surface forces, plus in addition to this we also have the body forces, which is acting on every point inside the domain. Sometimes, depending upon the extent of the analysis, we may also include energy equations, which contain again such a term for transient term. We also have the advection term, the velocity field transporting the energy into the domain. On the right hand side, we have the conduction term, which is transporting the energy through molecular agitation. There is no net transport of the fluid required for this conduction phenomena. That's completely based on the conduction properties of the fluid. And we may also have other sources of energy like pressure work, or in some cases chemical reactions also contributing to energy into the domain, heat being released or absorbed depending whether the reaction is endothermic or exothermic. In addition, we also have the equation of state, which is defining how the density is varying with pressure and temperature. So temperature you get from either from the energy equation, or if you define your problem to be an isothermal problem, so you get a constant temperature, and the pressure is something which comes out from the solution of continuity and the three momentum equations. We may also have sometimes properties varying as functions of temperature or even other quantities, but these may or may not be transport equations. These can very well be a simple let's say a linear equation or a polynomial function of temperature or other properties. So these are other equations which might also come up in a given simulation. Now when the flow becomes turbulent, That's when we say that the Reynolds number exceeds a specific value, because I guess you're familiar with this from the fluid mechanics lecture, that Reynolds number is a ratio of the inertial forces which try to keep, which try to, which the different molecules or different layers in a fluid possess, and it's a ratio of this inertial forces upon the viscous forces. Now it is this viscous forces which try to bind the different layers of a fluid in a flow, but it is the inertial forces which cause the layers to mix together. And when these inertial forces really dominate the viscous forces, that's when the flow becomes turbulent, very chaotic. And turbulence is quite unsteady and non-periodic, so there is no proper an orderly behavior of turbulent flows. So for modeling such flows, we can actually capture such flows if we can solve the Navier-Stokes equation exactly. Or even if we want to do a numerical prediction of Navier-Stokes equation, the task is quite huge because it's an unsteady phenomena, it's a non-periodic phenomena in space and time, and it's quite chaotic. So you can't really have a two-dimensional analysis. You can't really speak about a steady state analysis of a turbulent flow. And this requires a lot of computational effort. So people can't really afford in industry to solve turbulence to the minutest level of accuracy. So people have other ways in which they can model the effects of the turbulent flows, because as you can see some figures there that 10 points are needed to resolve turbulent eddy. If this is the condition with which we are going on, then we need something like 100,000 or zero point 0.1 million points to resolve just 1 cubic centimeter of space, and that's quite impossible if we are trying to analyze real industrial problems like boilers or process vessels, pressure vessels. It's a quite daunting task. So there are other approaches. We have something called turbulence modeling, which try to involve some time averaging of the Navier-Stokes equations. We get some extra terms in the process. I'll be discussing this, by the way, more in detail in the turbulence modeling lecture. But what we do is we try to modify the Navier-Stokes equation. We try to time average them. And there are some extra terms which come as a consequence of them, which we try to find out through some empirical relations, and this constitutes something called the turbulence models. This means we may have to solve, in addition to the equations, continuity and the three momentum, and in some cases energy equation, these are 5 equations. In addition to this, we may also need to solve additional turbulence model transport equations. So we'll see this more in detail, but you can just have an idea how the number of equations increases. From just being the flow equations, we may also include some turbulence modeling equations. Now that's an example of an incompressible Navier-Stokes equation. I'm just going to speak a little bit about it because we're just going to see what happens when we just neglect the viscous terms and we get the Euler form of equations. So that's the term where we have the transient term, we have the advection term. So the velocity field is transporting this property u, or in this case v or w, that's x, y and z momentum equations. And on the right hand side, in all these cases, we have the pressure gradient along x, y and z respectively, and also the variation of the x, y and z velocities, and that's the surface forces, and we also have the body forces along the x, y and z directions. So that's the overall set of equations we have, which is included in incompressible Navier-Stokes equation. In some cases, as you can see here, this body force term which you have here, this can be modified, especially for flows which involve natural convection. This body force might come up in the form of density variation, which according to a simplified model called Bozenisk model or Bozenisk approximation, it says that the density is varying only along one specific direction, which can be expressed as a function of temperature in this format. That's the Bozenisk model or Bozenisk approximation. And this is quite helpful in simplifying your overall problem setup. This is known as the Bozenisk model, and it's very helpful especially in buoyancy driven flows or natural convection flows. It's just an example what these body force term might look like in some cases. Now that's where we have the Euler's equation. The Euler equation, the continuity and the free momentum and the energy equation, they all contain the transient term, the advection term. Now that's the Euler equations. The Euler equation, they do contain the advection term, the transient term on the left hand side, But on the right hand side, what you can notice here in all these cases, the continuity and the free momentum and the energy equation, what you can notice is that on the right hand side we do not have the viscous term. So that's what Euler equation is all about. It's an inviscid solution or inviscid form of the general Navier-Stokes equations. When I say inviscid, there is no viscosity. But that also has some implications on the energy equation. You can see here in the energy equation there is no conduction term which has been included. So we are not having viscosity or thermal conductivity. So it's quite simplified and we can easily solve such problems, and this has been used for a long time for designing flight simulators and panel coat methods for ship simulations. So as I'm speaking about the different equations involved in CFD, we may also have situations where we are solving um, the motion of particles. In this case, actually it's the motion of, let's say, a particle being driven by the velocity field which is around it given by the fluid. So it's like a one-way coupling or two-way coupling. In some cases it's also possible. So what we are having is the fluid which is exerting a force on the particles, and if, let's say, the volume fraction of the particle in any cell or any given domain is quite little compared to the volume occupied by the fluid, we can apply something called the Lagrangian tracking of the particles. So the particles are solved in the Lagrangian frame, that is, I move with the particles, while the fluid equations are solved in the Eulerian frame, which is the conventional method. So the particle experiences certain set of forces called the body forces, which is because of the field in which it has been placed, and because of the velocity field of the fluid, it also experiences a drag force. So this is what the ordinary differential equation representing the velocity of such a particle looks like. So it has forces because of gravity, it has forces because of the drag, and this is all given by specific drag laws. And there can be also some other forces on the particles, like the Brownian motion force, or in some cases thermophoretic force because of temperature variation. There are also a lot of other forces like Safman force and still others which can be included. And actually such discrete phase modeling, or Eulerian Lagrangian approach as it is called, because the fluid is solved in the Eulerian frame and the particles are solved in Lagrangian frame, it has great applications for modeling sprays, or in some cases coal and liquid fuel combustion, and in some specific cases also particle laden flows, like we have a pneumatic conveyor. This can be solved by applying such an Eulerian Lagrangian combination. So in all these cases we can see we can also couple the droplet vaporization or the boiling effects, and for coal particles or some other fuel substances we can also include the devolatilization of such solid fuels, from which the volatile material gets devolatilized, gets vaporized into the domain out of the solid surface, and gets into the ambient where the combustion can take place. So a lot of advanced features are available in the standard CFD equations. In some cases we may also have different species being modeled within a given, let's say I'm speaking about a gaseous phase or a liquid phase. Within that phase I can have multiple species. I might have, for example, air being modeled not as a single species, but I might also include, let's say, air being consisting of nitrogen, carbon dioxide, oxygen, and many other constituents of air as a single phase. In the case of liquid, let's say we have a mixture of petrol and diesel and kerosene or different kinds of fuels, or let's say in the case of hydrophilic substances like hydrogen peroxide and water, we can have such mixtures. But these are single phase problems but consisting of multiple species. So we may have to solve additional transport equations for the multiple species in addition to the standard continuity, momentum, and the energy equations. So these species among themselves may or may not react. Depending on this, we may have a reacting flow, and it has many applications for combustion and also for fluid mixing. In reactors, we can include such multi-species modeling in addition to the standard four flow equations, or in some cases also the energy equation. Combustion model, again, we may also try to include some additional equations for combustion model. These usually come up as source terms in the different species equation and energy equation. They act as the source or sink of energy depending on whether the reaction is the combustion is actually the combustion is in most cases exothermic, but some cases we may have reacting flows where it is an endothermic process. So we may also include some sink in the energy equation. The PDF model, which is called the probability density function model, we may also include additional mixture fraction equations for the fuel oxidizer system, and combustion can be also modeled in this way. So you can see, in addition to the standard 5 equations, namely the continuity, the 3 momentum and the energy equations, we may also include a variety of other modeling equations for different applications. So it's very much dependent upon the problem you're trying to solve using CFD tools. That's the overall look at the differential equations. We have differential equations consisting of ordinary differential equations and partial differential equations. As was mentioned, ordinary differential equation consists of your dependent variables, let's say pressure, x velocity, y velocity, z velocity, or any other quantity, varying, or so to say dependent on only one independent variable. So we may have a differential equation in which your quantities, your variables, are being differentiated with respect to one independent variable. And that's an ordinary differential equation. So equations of the form du by dt is equal to function of time. So these are straightforward. There are standard analytical solutions possible. It's more about integration tricks that you can use. We may also have some more complicated functions of time. Let's say du by dt is equal to function of time, where the function of time can be as complicated as a combination of trigonometric and exponential functions. In such cases, we can use some standard software packages which actually involve some kind of numerical scheme to solve these ordinary differential equations. We can use some dynamic simulators that are available with commercial packages like MATLAB or Scilab. MATLAB has Simulink, and Scilab has, which is an open source solution, it has a dynamic simulator called XCOS, and they use methods like Euler's method or Ronchequata scheme in first order, second order, or fourth order schemes, with which you can find solutions to such ordinary differential equations. But for some simple problems, we can use hand calculations, and using some integration tricks, we can have analytical solutions. Now, partial differential equations, these are more complicated, and this is just what we encounter in fluid flow. In fluid or heat transfer, as you must have seen, because it's not just that the fluid is stagnant, but it's most of the cases it's dynamic. So we are having your fluid element getting distorted in space and time. And therefore we have the quantities like velocity or the pressure being differentiated with respect to not just time, but with being differentiated with respect to time as well as spatial coordinates. That's why it's more than just one variable. It's a time-space continuum that we are living in. So we have time as well as x, y, and z coordinates along which we are trying to have the variables differentiated, and that's how we get partial differential equations. Now these are more complicated to be solved analytically. It's quite difficult. Unfortunately, most of the time analytical solutions are impossible, but there are some tricks available also for some simplified partial differential equations. You can use some methods like combination of variables or Laplace transforms. So there is a very standard Rayleigh's solution of a boundary layers solution for such flow through a channel, for example. It's available. But in most of the cases, analytical solution is not what we try to use. We try to use numerical solutions, and numerical solutions are challenging and they require some additional steps. As you will see for finite difference, finite volume, and finite element methods, the additional step is the grid generation method. And that's what is also going to be taught as part of this course. On grid generation, you'll be learning some commercial packages, how you can discretize or divide or fragment a given geometrical domain or the domain of interest in which we want to solve the equations. We try to divide it into smaller fragments. That's called discretization of the geometry. And it is on this discretized geometry that you apply these finite methods like finite difference or finite volume or finite element methods.